Hello everyone. Today I am presenting our project on the design and simulation of log periodic dipole antenna using HFSS. Our antenna operates in the frequency range of 4 to 6 GHz. In this presentation, I will explain the antenna structure, working principle, and performance parameters such as return loss, bandwidth, and radiation parameters. When we come to LPDA antenna, the log periodic dipole antenna consists of multiple dipole elements of different lengths arranged in the logarithmic sequence. At a given frequency, only a few elements are active, and such the frequency changes, the active region shifts along the array. This unique structure allows the LPDA to maintain nearly constant impedance and gain across a wide frequency range. If we see the working principle of our antenna, the LPDA operates based on the concept of a frequency-dependent active region. Each dipole element is designed to resonate a different frequency. When the operating frequency changes, the element whole length is approximately half the wavelength becomes active. The alternating feed arrangement ensures the construction interface is the forward direction, resulting in the direction radiation. The mechanism enables the wide bandwidth and stable performance. If we see the design parameters, the performance of LPDA mainly depends upon the two parameters, the scale factor tau and the spacing factor sigma. The scale factor determines how quickly the element size decreases along the antenna. The spacing factor controls the spacing between adjacent elements. Here starts the parameters of our antenna. The first parameter is return loss. Return loss represents the amount of power reflects back due to impedance mismatch. In our design, the return loss remains below -10 dB across the operating band. This confirms good impedance match and efficient power transfer. The next parameter that we are going to discuss is bandwidth. The antenna operates from 4 GHz to 6 GHz. The calculated fractional bandwidth is around 40%, which clearly indicates the bandwidth performance. This bandwidth is achieved due to the logarithmic scaling of dipole elements. Now we will going to discuss about input impedance. The input impedance represents the ratio of voltage to the current at the feed point. Our efficient power transfer, it should match the transmission line impedance, typically 50 ohms. In our design, the input impedance remains nearly constant across the operating range, ensures the minimum reflection loss. The next parameter we are going to discuss is 3D radiation pattern total gain. The 3D total gain plot shows the directional radiation with maximum gain of approximately 6.2 dB. Radiation is concentrated mainly in the forward direction. Very little radiation is observed in the backward direction, indicating a good front to back end ratio. Now let's discuss about 2D radiation pattern total gain. The 2D radiation pattern at 4 GHz shows a clear main lobe in the forward direction and deep nulls in unwarranted direction. Both 5 planes show similar pattern, confirming stability and synthetic radiation characteristic. The maximum gain is around 6 dB. Polarization refers to the orientation of the electric field of the radiated electromagnetic wave. From the polarization radio plot, we observe stable polarization characteristics across the different angles. A strong peak near the main radiation direction indicates the dominant polarization in the forward direction. Deep nulls at other angles shows the suppression of unwanted polarization components. Overall, the LPDA maintains constant and stable polarization performance across the operating frequency range. Radiation electric field. The radiated electric field plot shows how the total electric field strength varies with angles. Maximum electric field intensity is observed in the main direction, confirming directional radiation. Deep nulls appears in unwanted direction, indicating minimal radiation where it is not required. The minimal behavior across different 5 angles observes stability radiation characteristics and efficient antenna operation. Power parameters. The power parameter plots include the incident power, accepted power, and radiated power. The incident power remains constant across 4 to 6 GHz range, ensuring constant input condition. The accepted power gradually increases with the frequency, indicating improved impedance matching. The radiated power is also increases smoothly, confirming the stable and efficient radiation across the operating band. Efficiency. Efficiency represents how efficiently the antenna converts input power into radiated power. Radiation efficiency increases the frequency and approximates nearly 100% near 6 GHz, indicating a very low internal loss. Total efficiency reaches around 95%, meaning mismatch and radiation losses are minimal. These results confirm efficient broadband performance of LPDA antenna. Directivity. Directivity describes how concentrated the radiation is in particular direction. The directivity plot shows a dominant main lobe in forward direction and deep nulls in unwanted direction. Peak directivity ranges between 4 and 6 dB, indicating moderate directional performance. The similar curves across different phi angles confirms uniform and stable radiation characteristics. Here we can see the various applications of our antenna like broadband wireless communication system, television and radio signal reception, and spectrum monitoring system. Here I would like to conclude the video. Thank you.